Uh, Okay, so today's lecture then is about randomized algorithms. Get you guys a little bit of exposure to randomization before the last homework is released tomorrow. So just the context of this whole week was two different senses of the word average analysis of algorithms. Last time was one sense when we did this amortized analysis, which was about kind of understanding a bunch of operations in the aggregate. So we can justify data structures that are almost always fast, but every once in a while, maybe do a lot of rebuilding or something like that. So that was average in the sense of the word that, oh, if I look at all the operations it's done, the average running time is always, very good or something like that. Even though an individual operation might have actually been bad. It's just that it didn't happen very often. Today will be a different sense of the word average because we're going to be looking at randomized algorithms that's going to flip coins to make choices. And then we can think of that as like a random experiment where you can run the algorithm again and again and again and again and ask, oh, what would the average running time be, or the approximation factor, or something like that. What's important about or an important distinction here when we talk about quote unquote average analysis is that we're still holding on to this sort of like worst case input kind of thing. So with the data structures, it's like, oh, in the worst case, no matter how someone uses the data structure, I'll still get these bounds. And today, it's still going to be like, oh, no matter the input, you'll still get on average based on the coin tosses, such and such a bound. But we're not actually losing any of the rigor of worst case analysis in terms of making an algorithm that's robust to any kind of input, which is really the most important thing, to have robust algorithms, especially if you're building, complex systems where you have many parts building on top of each other. You really need firm pieces. Okay, so all right, so here's sort of the plan for today. So maybe I'll start with the algorithms we'll do. We'll talk about 3SAT again and a quick approximation algorithm for it. We'll talk about a sorting algorithm called quicksort, and I'm going to introduce an algorithm called quickselect, the analysis of which will actually be left for you on the homework. Now, to be able to analyze these things, I'm going to have to do a bunch of intro sort of definitions and basic parts of probability. So some things we'll cover, what are events, what is a probability, conditional probabilities and stuff like that, the union bound. A big focus of today will be linearity of expectation and expected value. And then also like Markov's inequality. So there will be sort of, one half algorithm stuff and one half sort of mathematical preliminaries, some of which you guys have seen before, but in any case, not everyone has, or at least not recently. So it'll still be okay to do a refresher. I am kind of assuming that you've probably been exposed a little bit to some of these concepts before. Okay, so instead of kind of going straight into all the math definitions, it's a little dry. What I'm going to do is I'm going to introduce the algorithms first, then we'll go back, get through the definitions, and then we'll go back and analyze the algorithms with our new tools. So, all right, you guys know all about 3SAT, so I don't have to go through this slide too slowly. But we have a SAT formula with three variables per clause, three distinct variables. M clauses and variables like we've always done. This is sometimes thought of as sort of like a quintessential NP-complete problem. We now understand sort of the central importance of SAT, especially in completing this NP completeness stuff. All right, what we're doing today, which is a little different, is we're going to think about the related question of max 3SAT and trying to get the best possible solution. So we know that max 3SAT is the variation of 3SAT where you're just trying to satisfy as many clauses as possible. Of course, that's also NP hard, because if you can solve that, then you can figure out if it's satisfiable. But since it is NP hard, we won't try to get an exact algorithm, right? But in practice, you might still want an algorithm that does as well as possible, that satisfies as many clauses as you can. So we're going to try to do approximation algorithms. So something might be a like 1/2 approximation is if whatever the optimum value is, you can get at least half of opt. Okay? Alternatively, you might have like a 3/4 approximation if your algorithm can always get 3/4 of opt and stuff like that. So again, this is a situation where we probably won't get an exact algorithm because it's NP complete. But that doesn't mean that it's necessarily NP hard to get a good approximation algorithm, and it can still be very practical, right? We still want solutions, and we want the best solution we can get for these problems. So, yeah, approximating 3SAT, trying to get some approximation is not necessarily NP hard. If you can satisfy half the clauses or something, that doesn't really tell you if the whole formula is satisfiable. So it's not necessarily NP hard. Okay. So I was going to ask you guys, if you wanted to approximate a max SAT problem, so I give you a 3SAT formula, and your goal is to come up with some algorithm that tries to satisfy as many of the clauses as possible. But you're probably not going to get an exact algorithm. What ideas might come to mind? Any heuristics? What would you do? Yeah. Randomly assign what? Okay, like what? Sure. So we'll try many combination randomly. Give me one combination, just any combination. Well, just any concrete ideas to make it more specific to help us out. What would be an example of a combination? Or how would you come up with a combination? Okay, so for x1, you want to randomly assign one, x2, randomly assign one. So it's just a uniformly random sample? Okay. That actually is what we'll analyze. Usually people suggest like more clever things first, okay? And then I say, oh, what about silly ideas? Anyway, here maybe is the silliest possible approximation algorithm that I can think of, right? So I'm given some formula. I want to satisfy a bunch of clauses. For each variable, I'm going to flip a coin. For x1, if it's heads, I'll give it true. If it's tails, I'll give it false. And I'll do the same thing with x2 and x3, x4, x5. So at the end, I have a completely random assignment, right? Completely random true, false. And it'll satisfy some clauses if we get lucky, and maybe it won't satisfy others. And of course, I can repeat this algorithm a few times and see if, I get lucky the second or third try or whatever. The point I want to make is that this is a ridiculously dumb algorithm. It roughly takes into account no consideration of the actual SAT formula. It doesn't look at it at all, right? It just obliviously assigns true, false, true every variable. I can't think of anything dumber than this algorithm in some ways, right? It just doesn't pay any attention to the input. Okay, so we're going to analyze this. And here's what we're going to do. We're going to show that this very silly algorithm is a 7/8 approximation. So it's going to get at least 7/8 times opt, where opt is the maximum possible satisfiable. Okay. We'll also figure out how to take that obviously very random algorithm, flipping a coin for every single one, and turn it into a deterministic algorithm inspired by the random one that doesn't use any coin tosses at all. So we'll deterministically be able to get 7/8. Okay. And then what we won't prove because it's way too hard. But what's sort of amazing is that we think that this algorithm is the best possible algorithm for max 3SAT. So there's something called the PCP theorem, which we discussed a little bit in the randomized class. But for this particular case, it states that for any epsilon, like say 0.001 or something, getting a 7/8 plus 0.001 approximation is NP hard, or 7/8 plus 0.00001. Anything strictly better than 7/8 is NP hard. Okay, so in fact, there is also a limit to approximations as well. You can't always get like arbitrarily good approximations for all problems and stuff like that. There are sometimes these thresholds where beyond this point, it becomes NP hard. So this is all just like a pretty spectacular picture that ridiculous algorithm is actually the best we can do unless P is equal to NP. Okay, so we'll analyze that today. Second application is quicksort. Maybe many of you have seen this algorithm once before. All right, so we did this a lot. We're sorting. I'm giving you n comparable elements. You want to list them from smallest to biggest. Merge sort takes n log n time. We even have a lower bound of n log n, so you can't really do better. Now merge sort, well, here's maybe an algorithm that I would argue is relatively simple, maybe silly, compared to merge sort. Okay, so you have your big list of unordered elements, right? And I'm just going to pick one of them randomly. And I'm going to make two piles, everyone that's smaller, everyone that's bigger. Okay, and I'm going to recursively sort both halves and then kind of glue them together. Okay. So this is called quicksort. It's a very simple algorithm. I'm just randomly picking an element, dividing in half, recursing. Can't think of anything simpler than that. So you can think of it as sort of like a randomized divide and conquer algorithm, right? So I guess I'm just drawing on pictures what I wave my hands about. But step one, we pick a random element as a pivot. We'll divide it into both parts, right? I'll recurse on both sides. That means it's going to pick more random pivots and put it all back together. All right, very simple, kind of very intuitive. The only kind of wrench thrown in there is that I picked the pivot uniformly at random, and we've never analyzed anything like that before. That said, it might even be what you do in real life. I feel like you probably wouldn't do merge sort because that's like very unhuman. But in real life, you might actually just like pick a random number, split it in half, and then give one half to your friend or something, like, okay. All right, so we'll analyze this algorithm. We're going to prove it takes n log n time on average. So on average, it's going to match merge sort. We'll also prove something stronger. We'll show that it'll take at most n log n time with really, really high probability. Like you'll get struck by lightning before this thing is much slower than n log n. Okay. So perhaps this is why, well, yeah, it's such a simple algorithm, and it gets good average performance. And this is actually a very popular choice for sorting in practice. For a long time, the Unix sort subroutine was using quicksort. Okay, so sometimes given a few different algorithms with the same asymptotic running time, the simplest one with the least amount of code tends to be very fast in practice. It has better constants. Yeah, so why would you use this instead of merge sort? So one, I think if you're coding it, this is way easier. You don't have to do that silly loop with like I, J, and you're like merging things together. And then second, probably you're never going to really see it ever be much slower than n log n. We'll prove that. Just how strongly concentrated the running time is at n log n. Yeah, simpler implementation, and I think that we don't focus on this too much because it gets more detailed than is interesting. But if we really were worried about sort of the hidden constant, you know, is it 10 times n log n, 100 times n log n, and stuff like that. The simpler code usually translates to a smaller constant, right? Because the more complicated code just feeds into the constant. So at the end of the day, people do actually implement these and they just test them out. And then they find, oh, quicksort's actually really fantastic, besides being easy. And I guess the best explanation I have is like, oh, that makes sense because the code is quite a bit shorter than merge sort. Okay. Um, okay. And then probably in real life, you're mostly observing the expected running time anyway, because you just run it over and over and you don't pay too much attention. So, okay. All right. The last algorithm is maybe more compelling than quicksort because merge sort's relatively simple. So this is for the selection problem. So, now you have a big list of unordered elements and you want to say find a median or find the 10th biggest element or n over 10 or whatever, right? The rank k element for a given index k. So this is the thing that we use that crazy median of medians algorithm to solve, which is a complicated divide and conquer algorithm where, you like broke it up into groups of 5 and you got all the medians and you got that kind of complicated thing. All right. So the main takeaway from median to medians is that, okay, it was definitely not easy. It was a non-trivial algorithm, non-trivial to analyze, non-trivial for me to draw pictures. Right? It took me a long time to make slides. That's how I measured the complexity of an algorithm. Okay. Here is a sillier, simpler algorithm. Okay, kind of like what we just did. So I have a bunch of unordered elements. I'll pick one of them uniformly at random. Okay. I'll divide it into two piles, the elements that are smaller, the elements that are bigger. And I'll figure out the rank of the element at the same time, right? So I'll take that element and I'll compare it with everyone. I'll find out, oh, this is the 10th biggest element. Oh, it's the 100th biggest element, whatever. Right? And based on the rank of my pivot, well, if I'm lucky, it's the kth one, but probably not going to get lucky. Based on the rank of the pivot, I'll say, oh, I need to go to the left pile, or the right pile. Okay, so you figure out which side to recurse on, and you recurse, and you eventually get the rank k element. Okay, so I think this one is clearly much simpler than median and medians. Maybe merge sort because you guys know it. I've known it for so long, it's not as convincing. But this is obviously much simpler than median medians, and this is actually much faster than median medians in practice. So I think here the appeal is more clear. Okay. So on the homework, yeah, the algorithm, it doesn't matter. Okay. You'll show on the homework that this algorithm takes linear time and expectation, matching the median to medians algorithm. Okay. And at least one way to do the analysis kind of is very similar to quicksort. So hopefully you can take what we did for quicksort and figure out how to apply it. All right. So those are the three motivating applications for us today. We'll have more in the coming weeks. But now I have to run through like a bunch of math definitions and stuff so that we have the tools to analyze and kind of concisely describe what we want to describe. So, I know a large number of you are more comfortable than others, but it's okay. All right. All right. So if I flip a coin and I ask you, is it going to be heads or tails? What would you say? What's the most you can say about the coin? Yeah, you don't know, right? You don't know if it's going to be heads or tails. That's the whole point, right? Okay. On the other hand, you might say a statement like, half the time it comes up heads, right? And that's a statement we're all like very comfortable with. I think we all know exactly what that means. But if you think about the phrase, it doesn't make a ton of sense, because there's only one coin. What does it mean half the time? There's only one outcome, right? But nonetheless, you know exactly what I mean when I say half the time. So when we say half the time, we're already like immediately using our imagination. We're immediately thinking, oh, if I had, done this experiment in a million parallel universes or something, or I was in a million different rooms sealed off from each other, then I expect about 500,000 to come up heads and 500,000 to come up tails. Even though it may never exactly be 500,000 heads, 500,000 tails. Nonetheless, I don't think this is all like should be common sense to you guys, right? So you guys are already immediately kind of vaulting into mathematical abstraction, even in kind of standard parlance. So that's, just probability theory, right? So probability theory is assigning uncertain events values between 0 and 1. This is the probability of the event occurring, right? And then it's not, probability theory is actually very simple. There's only like a few rules. And the only tricky part is somehow just sticking to the rules, especially when things get more complicated. But otherwise, the rules are really simple, and I hope to convince you that the rules should all roughly be kind of common sense if taken, in small, slow steps. So here's one rule, right? For every event A, like coin comes up heads, there's some complementary event, which we often denote with bar A, of the event not occurring. All right, the coin comes up heads. The complementary event is the coin doesn't come up heads, which is just tails, unless it lands on its side, which usually doesn't happen, right? And so the probability of these values between 0 and 1 obey the rule that, oh, the probability of event occurring plus the probability of event not occurring is exactly equal to 1. Okay, because one or the other has to happen, and they never happen at the same time. Okay, so that's one simple rule. Okay. So besides events, you can talk about combinations of events. So a common one is two events simultaneously occurring. You might have event A, event B. A and B describes, oh, event A occurred and event B occurred. One coin came up heads and the other coin came up heads. Okay? So in combining events, I get a new event that describes their conjunction. Okay? So you have, for any two events A and B, you have like four combinations. I can have A and B occurs. I can have A occurs and B doesn't occur. I can have A doesn't occur, B occurs, and I can have neither of them occur. And those four combinations, A, they're exhaustive. One of the four must happen. And they're exclusive. None of them will happen at the same time. So their probabilities are always going to add up to 1. All right. Another simple thing. I have two events A and B. If A has occurred, B either occurs or it doesn't occur. Okay? So probability of A and B occurring plus the probability that A and B doesn't occur. A occurs and B doesn't occur is just the probability that A occurs. Because within sort of the scenario where A occurs, B does or B doesn't. Okay. We can also talk about conditional probabilities. If I know A has occurred, what are the odds that B occurs? What is the probability that B occurs? Okay. And that's always given by, you can kind of imagine like taking pieces out of a pie. Out of the total probability of which A occurs, what is the probability that A and B occurs? That fraction. So that's why we write probability of B bar A, we think of as probability of B given A. What's the probability of B given A has occurred? It's the fraction, the probability of A and B occurring divided by the probability of A occurring. Okay. Right. Right. Okay. What else is going on? Okay, so in general, like the probability that B occurs given A has occurred is not necessarily equal to the probability of B occurring kind of independent or irregardless of A. Okay? But when that does happen, that means those events are independent. Okay, so let's see. What are some simple examples? Well, we have one coming up, but if I have two different coin tosses and the first one comes up heads, then the second one is going to come up with heads, still with probability 1/2. It doesn't depend on the first coin. Okay? But if A and B were both describing the same coin, then it's not independent at all. Once event A happens, then event B always happens, since we're talking about the same coin. Okay, besides conjunctions of events, you can also have unions of events, right? A or B occurs. That describes another event. I think the most important thing, or really important tool when analyzing the union event. So this is actually going to happen to us a lot in algorithms because algorithms can be complicated. Plus the input is like adversarial and we don't assume too much. There's just like a lot of events floating around at the same time. So we often find ourselves analyzing the union of various events and it's kind of hard to detangle them. based on the information we have. It's just like too complicated or we don't even have enough information. So we often use this really simple inequality called the union bound. Okay, so in general, well, okay, so the proof is above it, but if A or B occurs, there's like three possibilities. A occurred and B didn't, uh, A didn't occur but B did, or both A and B occurred. And you do some simple rearrangement, but you'll conclude that the probability that A or B occurs is at most the probability that A occurs plus the probability that B occurs. Okay? So that gives you a really simple union bound on the union of any two events. All right. I think some people have literally fallen asleep, so I'll try to keep going quickly. Um, okay. All right. So much for events. So in addition to events, we also have random variables. Okay. So these are like, whereas events are sort of like a Boolean thing, something happens or it doesn't. Random variables are like numbers, random numbers. So you roll a dice, it's a random number between 1 and 6. Okay. You know, the event or saying that, oh, the dice returns 4 is an event. So for a random variable in a particular value, x is equal to the value is an event, and you can analyze it accordingly. Okay. All right. So some examples of random variables. I guess a coin toss you could think of as a random variable that can take heads or tails. Okay, and it takes each one with probability 1/2. I guess the other example is a dice. It takes one of 6 values, each with probability 1/6. Okay. All right. So now, what happens when we want to do something like what happens when we have 2 random variables, like 2 dice or something? Then you start having joint distributions, right? Distributions depending on the value of the first dice and the second dice. So, to formally define it, if you have 2 random variables x and y, then sort of their pair, their tuple, x comma y, can also be thought of as a random variable. Okay, so you can combine random variables very easily. In general, just to draw attention to the last line, the probability that like a random variable x is particularly equal to one value and a random variable y is equal to another variable, another value, is not equal to the probabilities taken separately. Okay, because the random variables may depend on each other, so don't always make that assumption. All right, let me find something more fun. Okay, when the probabilities do split up, that's called independent. Right. Okay. Right. Okay, so here's a silly example. I kind of just said it a moment ago, but I'll go through it again. So you can have 2 random variables, x and y, modeling coins. They take values heads or tails, right? If x and y are modeling 2 different coins, then those events like heads, 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 tails, tail heads, and tail tails each occur with probability 1/4. Okay? And of course that's kind of simple enough. If x and y were of course modeling the same coin, then this is no longer true, right? If x and y were both modeling the same coin tossed up, then it'll be heads, heads with probability 1/2, and tails, tails with probability 1/2. And then the other combinations can't happen because it's the same coin. This is like a silly example, but actually the latter case sort of happens more than the former, or rather deep inside an algorithm, you have all these parts moving, like imagine you're taking random pivots for a quick select, but choosing one pivot affects future pivots, affects future pivots, affects future pivots. So in general, we rarely have the case where, oh, they're completely different coins and they're independent and I can directly break things up. We often find ourselves being like, I can't really assume independence. And you're kind of looking at the second, more pessimistic scenario. All right. All right. Here's, I think, the most important part of the class or today. And when we talk about random variables, we're talking about quantities. which allows us to talk about averages. So the expected value of a random variable x is is sort of the average. Yeah, it should be, shouldn't it? I feel like I used these last semester. Nobody said a thing. Okay, one person's awake. All right. Okay, so average, first of all, you already kind of understand what an average is, but if you wanted to kind of write it out numerically, what I can do is I can sum over all the possible values, okay, and say, okay, with probability 1 in 5, it gets value 10. So I'll add 1 over 5 times 10 to the sum, and I'll go through all the values, right? So if you're doing, oh, I have a six-sided dice, what's the average? It'll be 1 times 1 6 plus 2 times 1 6 plus 3 times 1 6 all the way up to 6. And that'll give you something. 3.5, maybe? Okay. So, all right, so that's the expected value, right? Which you guys already know, but hopefully this class will teach you something. Okay. The most important kind of or one really nice thing about expected values is this thing called linearity of expectation. Okay. Suppose I have two random variables x and y, and I want to say what's the expected value of x plus y. So I want to know the expected value of the sum, right? And I don't know anything about how x and y are related. Maybe x and y are both modeling the same dice or same coin or whatever, right? They can be related in some complicated unknown way. But linear expectation says no matter what, I can separate them when it comes to calculating averages. So the expected value of x plus y is equal to the expected value of x plus the expected value of y. Even if x and y are completely related to each other. No matter what mysteries are going on, I can actually separate it. And in your context, it might be much easier to analyze them separately. Actually, all our examples today will be about how they're easier to analyze separately. So this is a really, really valuable way to take like a really complex phenomena, like will arise in a randomized algorithm, and be able to break it up into very small, manageable components. In fact, it's almost the only way. That and like the union bound. They're both relatively simple and crude, uh, but because of their simplicity, they're actually incredibly useful. Okay. This doesn't end. Okay. You can have conditional expected values. So conditional on something happens, what's the average? And you get the same definition, except now the probabilities are conditional on the event happening. Okay. Um, right. Okay. All right. So I snuck in one puzzle because I knew you guys would be super bored at this stage. So, okay. This is just to make sure we're kind of on the same page, and it's also a very valuable problem as well. This comes up in one of the homework problems. All right. So for simplicity, let's say I have a fair coin, right? It comes up heads is probability 1/2. Imagine I keep flipping the coin until I get a heads. What is the expected number of coin tosses? Well, I have to toss at least one. Oh, 1 over p. Okay, so sure. So 2 for 1/2. Why? How can you prove it? It seems intuitive because 50% of the time. So if you're going to guess something, you probably would have guessed 2. But how do you prove it? Okay. Okay, that's appropriately vague where you're neither right nor wrong. But let's say that X is the number of coin flips that you make, right? So, you have some randomized experiment and it'll be assigned a value 1, 2, 3, 4. Okay. All right, so you said expected value, so I'll just write expected value of X. Okay. And then? Oh, okay, so you're going to do like summing over 1 to like infinity, 1 plus 1/2 plus 1/4 plus, and so forth. Oh, no, no, this is not right, right? Okay, one sec. Good. All right. So if we calculated linear of expectation directly, so maybe I won't write it that way. Okay. We would say, okay, what are the odds that it's one, right? The odds that the answer is one is, oh, you get heads on the first try. That occurs with probability 1/2. So it'll be 1/2 times one plus now what's the probability that is two? The only way to get two is 1/2 times 1/2. So you get 1/4 times two. And now how do you get third? How do you get three? You have to get one tails, tails, heads. Okay, so you get 1/8 times three and so forth. So you get a bunch of like I over 2 to the i's. Okay, and this seems like a pain to work with. Okay, anyone have a different proof? Okay, so let's say that, let's go more slowly. All right, the expected number of coin flips, okay, is, all right, half the time you get heads and it just becomes one. And then half the time you get tails. So you flip one coin and then you conduct the rest of the experiment. The first coin toss is tails. Okay. Um, oh no, no, no. Okay, sorry. Let me go more slowly. Okay, so the expected value of x given that the first one's head is just one, so I put a one there. Okay. And given that it's tails, well, okay, x given that it's tails. All right. So one way to think about this is, okay, so first you get one for the tails, right? And then after the tails, you're going to keep flipping coins until you get heads, right? And the expected number of tosses you're going to do is sort of like starting the experiment all over again. Okay? So let me write this just differently from the start. So if you get tails, you have flipped one coin plus the remaining number of coin tosses is like the exact same experiment all over again. Okay? So I have 1/2 times 1 plus 1/2 times 1 plus expected value of x. And if you solve this, I think you'll get something like 1/2 expected value of x is equal to 1, and you multiply both sides by 2, and you'll get 2. Okay? All right. So with this, you would be able to kind of, in the same way, figure out how to do different p's. If I told you that it flips heads, it's probably 1/4 or 1/10, right? Let me give you another one just for fun, in case you find this fun. What is the expected number of coin tosses until you get two heads? Say for a fair coin. A bit more complicated, right? What's the expected number of coin tosses until you get two heads? Okay, why? Well, I want a better answer than that. What's the slick way to see that it should go from two to four? We'll have what? Oh yeah, not in a row though. Just two heads total. Uh, yeah, okay, so let's put it this way. What we'll do is we'll define x1 to be the number of coin flips before the first heads. And x2 will be the number of coin flips between, like after the first heads and until the second heads. Or maybe I should write until. Between first and second heads. So we're running out of space. Okay. All right. So the quantity we're interested in, x1 plus x2, together will describe the total number of coin tosses until you get heads, two heads, right? X1 is the number of coin tosses until the first one, and then x2 is how many more until you get the second one. They're both random quantities, right? But here's what's great. Because of linearity of expectation, I'm allowed to write them out, right? It justifies analyzing them separately. The average of the sum is the sum of the averages. Okay. Now x1 is that first experiment. Oh, how many coin tosses until you get a heads? X2 is the same experiment. How many coin tosses until you get a heads? So each of them is just two. Okay. But we're not, it's so much simpler because we're doing averages. That's the point. Okay. All right. Yeah, no, nothing too big a deal here. You know, we can have expectations over two random variables in general or some function of two random variables. That would be kind of the formula. And here's a trick that comes up kind of nicely. Suppose I had two random variables x and y, and I wanted the expected value of x. I know it's kind of abstract. But somehow, calculating the average value of x is somehow difficult for some reason. But sometimes they have a second random variable y where conditional on y, it's easier to calculate the average of x. Then the expected value of x is equal to the expected. Okay, let me go through an example. All right, suppose I want to know if it's going to rain tomorrow. Okay, that's what I want to try to predict. What's the odds it rains tomorrow? And suppose in general that's hard to predict, but it is easier if I knew it was raining today. Maybe if it's raining today, the odds of it raining tomorrow goes up. And maybe if it's not raining today, the odds of it raining tomorrow goes down or something, right? So based on the information of whether or not it's raining today, it's easier for me to calculate the odds of it raining tomorrow. Okay? Now, okay. So the law of iterated expectation says that if I know the probability it's going to rain today, and maybe I do because I know today's weather report, and I'm able to calculate what's the probability of it raining tomorrow depending on whether or not it rains today, then I can figure out the probability that it rains tomorrow. Okay, I think the story is more useful than the formula. Okay, all right. So these are all things that'll come up at some point in the lecture, and that's why I have to do it. This is the last thing I promise, but this is also really important. This is called Markov's inequality, and I'll give you a simple analogy. All right, let's say that on our midterm, the class average is like really low. It's like 30. I'm not saying it is. That's never happened before, but let's say it happens. Okay? What percentage of the class can get at least 60% on the test? If you knew the average was 30, what percentage of the class can get at least 60% on the exam? Sorry? Almost half the class can get 60%. Because that one half of the class times 60 will already give you 0.3, and that's the average. Okay, so in general, whatever the average is, at most half the population can get twice the average. So if the average number of points scored by a player in the NBA is like 5, at most half the league can be scoring 10 or more points. And at most 1/3 of the league can be scoring 15 or more points. Okay, so that's sort of common sense. That common sense is called Markov's inequality. Okay. And it's not so hard to prove. Okay, so right. You just kind of break down. Okay, so I say, okay, what are the odds that x is bigger than some given value alpha, right? We can break down the expected value of x sort of by conditional probabilities. Like, okay, what's the expected value of x given that x is at least alpha times probability that x is at least alpha? And what's the expected value of x given it's less than alpha times the probability it's less than alpha? Okay. And what we could do is, since x is non-negative, right, I could say, well, this quantity is at most 0. Okay. While this quantity up here, because conditional on x being greater than alpha, this thing is at least alpha. So you get this alpha times probability x is greater than or equal to alpha, and then you just rearrange it, you get Markov inequality. So there's nothing too special. I mean, you can just think of it as, at most half the class can get twice the class average. Okay. All right, now we're done. So everyone come back to class. All right. Formally, I have to define these things to do the algorithms. Okay. All right. So now let's go back to more fun stuff. Let's talk about algorithms. We'll start with 3-SAT. So just to remind us, 3-SAT, you guys all know, we're analyzing this very simple, silly algorithm where every variable I'm assigning true or false, which apparently is the best possible algorithm for this problem. Okay. All right. So the algorithm again is really simple. I'm assigning every variable true or false. And I want to argue that it gets a 7/8 approximation. So we're going to start really, really small. Suppose the formula had only one clause, okay, with just 3 variables, x1, x2, and x3. What are the odds that I satisfy that clause? 1/8? Okay, how do I satisfy it? Let's say that example. Okay, that will satisfy it, but what if x1 is false, x2 is true, and x3 is false? So it is an or, not an and. So you actually only need one of them. Okay, 7/8. Why 7/8? Sorry? Give me something simpler. Why 7/8? Many people say 7/8. There's only one way to falsify it, which is the exact opposite of what you suggested. Well, yeah, you just had a bit flipped. So if it was false, false, true, then it wouldn't be true. But otherwise, it'll be satisfied. So out of the 3 coin tosses, there's only one combination that's going to satisfy this, not satisfy this formula. So as a result, we get, okay, the probability I satisfy this clause is 7/8, so I'm satisfying 7/8 of the clauses. Okay, that's simple. So simple to analyze one clause. That's because just 3 coin tosses. And roughly it's what are the odds of getting at least 1 heads out of 3 coin tosses. All right. What if I had 2 disjoint clauses? Right? So 2 clauses that had nothing to do with each other. How would I calculate, like how many I'm going to satisfy and stuff like that? What are the odds I satisfy both of the clauses? A 7/8 squared. So now the clauses are completely disjoint, right? So I satisfy the first one is probability 7/8. And those coin tosses have nothing to do with the coin tosses for the second one. So that's probability 7/8. So if I wanted to directly calculate the expected number of clauses I'm going to satisfy, you would get 7/8 squared times 2. Those are the odds of getting 2. Plus, in order to satisfy one of them, I can get one of them right and the other one false. So that's 7/8 times 1/8. Or I get the second one right and the first one false. So 1/8 times 7/8. So that's 2 different ways. 2 times 7/8 times 1/8 times 1, and then otherwise it's 0. Okay. So what do I get if I add these up? Is that what you guys got? Okay. Let me make it a little bit more complicated. Suppose instead of having two completely disjoint clauses, they should have one variable in common. So in this one, they both have the variable x3. Now suppose I ask you a simple question like, what are the odds that both clauses are satisfied? Right? Which was sort of like the first step of our calculation. Now, the only difference from before is that they share one variable. What are the odds that both clauses are satisfied? Okay, so what is it? Calculate it. It's clearly more complicated, right? All I did was introduce one variable. This is not a complicated formula. It's two clauses, five variables, and I overlapped one variable, and suddenly it's a huge pain. And if you wanted to do it, you can do something like, okay, so with probability 1/2, x3 is true, right? And then you get both. And with probability 1/2, x3 is false. And now each one comes down to two coin tosses. So each one has a 1/2 chance of being right. So that means on the first case, you have a probability 1/2 of just x3 being true, plus 1/2 times 1/2 times 1/2. So 1/8. So you get like 1/2 plus 1/8 chance of getting them both correct. Okay. But clearly it's a bit more involved than last time is really the only point I want to make. Okay. Now what if I, gave you three clauses that have some variables in common, right? Again, this is not a complicated formula. There's only three clauses here and six total variables. But if I ask you a question like, what are the odds that all three clauses are going to come up correct? It's quite painful, right? Okay. So now imagine trying to do a lot more, right? Uh, it's basically hopeless, right? Okay. So now I want to calculate, at the end of the day, I want to analyze this algorithm, but the key point is that I only want to try to analyze this algorithm on average. So let's kind of make the question more specific, right? Okay, well, yeah, okay. Okay, yeah, so this is quite common, right? Is that this algorithm is doing a bunch of different stuff and it's basically impossible to analyze directly. This happens always. So, all right, suppose I only wanted to calculate the average, right? If I only wanted to calculate the average number of clauses being satisfied, then we have one incredibly powerful tool at our disposal. That's linearity of expectation. Okay? So let's see how that helps us. So what we're going to do is we're going to make a variable for every clause. Okay, so for the first clause of a variable y1, it's equal to 1 if the clause is satisfied, and 0 if the clause isn't. Okay, so 1 if it's satisfied, 0 if it isn't. So just saying whether or not the clause is satisfied. If I sum up the yi's, then I get the total number of clauses that are satisfied. Okay. Eventually, we want to figure out the sum of yi's, but let's just do one yi first. What is the expected value of yi for a particular I, for a particular clause? 7/8, because there's 7/8 chance of being satisfied, and you get 1. All right, so that was very easy, right? Oops. Okay. All right, so that's very easy to analyze one. Now, if I want to get the expected value of the total number of clauses satisfied, right, which in our variables can now be written as the sum of yi's. All right, this is where it gets hard, right? It's only when I analyze combinations of things where life gets difficult. So how do I approach this? What do I do now? So the expectation of the sum is the sum of expectations, right? So it's the sum of the individual expected value of yi's, which is very easy, right? You guys answered immediately that each one is worth 7/8. Okay? So you get 7/8 m. It's actually very easy. Anyway, we're trying to directly analyze even three clauses. It's like impossible. But if you're only worried about the average and you're only worried about things in the aggregate, you can use linear expectation, break things apart, and analyze them as if the clauses had nothing to do with each other. Okay, so in this way, you can take a really complicated phenomenon and actually make really precise statements. We're not saying that the average is at most 7/8. We're saying it's exactly 7/8 m. We lost nothing in the calculation. There's no estimating, right? This is an exact calculation, right? So linear expectation is very powerful. All right, let's try to de-randomize this algorithm. Okay, so the algorithm is very random, right? It's tossing a coin for every random variable. And we're going to use this to inspire an algorithm that doesn't toss any coins. All right, so here's the random variables from just like before. Yi is 1 if the clause is satisfied, otherwise 0. And I'm letting z denote the sum, which is the number of clauses that are actually satisfied. So these are all randomized quantities, right? So we're going to imagine we run the randomized experiment, but we won't actually. But you want to imagine it as a thought experiment. Now, oops, okay. So I can take the expected value of z and I can break it up using conditional probabilities, right? So the expected number of clauses being satisfied is equal to, it was probability 1/2. The first variable is assigned true, and then there's some expectation based on that. And it was probability 1/2. The first variable is assigned false, and there's some expected value based on that, right? So I'm just using conditional expectations. Nothing really magical has happened. This is just kind of that basic rule. Okay, but what's great about this formula, right, is, well, yeah, those two quantities on the right. One is what happens if x1 is equal to true, and what happens if x1 is equal to false. If they're both really small, then the expected value of z would have to be small in general, right? But expected value of z is actually pretty good. It's 7/8 m. So what does that say about the bigger of the two values? Well, okay, so one of those two conditional expectations, the expected value of z given that the first one is heads, or the expected value of z given the first one is tails, at least one of them has to be 7/8 m, right? So one of those conditional averages has to be at least as good as the general average. Okay. All right, so we actually know, okay, so what does that tell you? That means that either setting it to be true or false, one of the two choices must be good in the sense that it gets you at least 7/8 m. So, okay, one of these two choices is good, right? Now we want to figure out which one, because then I just have an algorithm that just figures out which one is good, right? Okay, so how can I try to figure out which one is good? So either setting x1 to be true or setting x1 to be false will preserve that average. How do I figure out which? We can what? Okay, we can try to see which one satisfies the most clauses immediately, right? But that doesn't necessarily, that's not always a good idea. Otherwise, Otherwise, the overall algorithm would just be some greedy thing of like, oh, pick x1 to satisfy the most, x2 to be satisfied. Because maybe x1 setting it the other way will satisfy some clauses that are otherwise very hard to satisfy. So, yeah, so that's not quite it. But that's actually a good point of contrast. That's what, many people suggest. Okay, so at some level, if I can calculate these values, then I can pick the bigger one, right? If I could just set it to be true and then figure out what the expectation is, then I can just pick the bigger one of the two. So how can I do that? How do I calculate these values? Yeah. Yeah, so if I do set it to be true, maybe some clauses will be immediately satisfied. Some clauses will go down to two variables because it had x1 false. And other variable clauses will stay the same. Right? So I can kind of figure out the residual formula. And then how do I calculate the average? Yeah, we can do it just like before, right? So the expected total sum, given x1 is equal to true, I can use linear expectation again, right? And it's the sum of the expected value of each of the clauses, given that x1 is equal to true. So I find myself just analyzing a lot of individual clauses again. This is pretty easy, right? So if a clause like had x1 in it, then it's automatically 1. If it didn't have x1 in it, it's still 7/8. If it had x1 bar in it, then now there's only two variables left. So it becomes like 3/4 or something like that, right? So it's easy to calculate um, each of these values. Okay, so we can actually calculate, we can just directly calculate which one is better between these two choices of setting x1 to be true or x1 to be false. Okay. And now that leads to an entire algorithm. So I choose x1 just by recalculating the average directly. And then I can figure out x2 based on conditional expectations and x3, right? So the induction step is nothing too special. I've already chosen 10 variables, so the average is still very good. And now I can use conditional expectations again, right? So I've already figured out 10 variables, and then I say, okay, the 11th variable is either true or false. I use conditional expectations again, and I'll calculate all those values and figure out the better choice. Okay, so you can just figure them out one by conditioning on your choice and calculating the new average. So that's the entire algorithm, the deterministic algorithm. Okay, so that really silly algorithm leads to a more kind of sophisticated looking deterministic algorithm, which is really just de-randomizing that randomized approach. Okay, it's also a nice example of kind of using conditional expectations. Okay, good. I think we have enough time to do one more algorithm, which is quicksort. Any questions though about what we just did? All right. All right, so the quicksort algorithm, I think you guys remember, but it's pretty simple. Bunch of unordered elements, pick one of them, figure out what's smaller, what's bigger, and recurse. Okay. Okay. So let's first try to figure out how to show this takes n log n time and expectation. If you don't have time for high probability, oh well, life goes on. Okay, check the notes, but we'll probably have time. But the expectation is the most important part, so let's do that. All right, so if I wanted to analyze this algorithm and like try to write a recurrence for it, it's a little bit weird, right? So it is divide and conquer. So I would think, oh, I can write a recurrence. But the thing is, where it's dividing is kind of like unclear, right? So in general, I might write like, oh, it's like I have k minus 1 elements on one side and n minus k elements on the other, where k is some random value between 1 and n, right? If I take the 10th biggest element, there's 9 on one side and n minus 10 on the other. If I take the 11th and so on, right? But it's a random value in between, right? And it's like, oh, geez, what am I going to do? Okay, so you could try to put expected values around this whole thing. And there is a way to do this, but it's quite painful. Okay, so we're going to try to do a different approach. What would be like the best choice of k, right? So in general, k could be anything, but what would be ideal? The median, I guess. So we would always pick like something right in the middle, and split the input in half, right? And if you did, then you'll get something, T of n is equal to 2Tn over 2. That's sort of like merge sort, plus big O of n. You get your n log n, right? So if you could split them in half, that would be great. What's the worst case? The best case is right in the middle. What's the worst? Yeah. Oh. Yeah, at the extremes. If I always pick the smallest one, I have n minus 1 elements left, and then n minus 2, and then n minus 3, and I'm hardly making any progress. So in the worst case, right, then you have some recursion that looks like, oh, T of n is equal to T of n minus 1 plus big O of n. So roughly the running time looks like n plus n minus 1 plus n minus 2 plus n minus 3 all the way down to 1. That's roughly n squared. Okay. All right, so in the worst case, you're always stuck at the edges. In the best case, you're in the middle. And the question is, which one is it? Right? I'm trying to analyze this thing. Oh, should I assume the best case? Should I worry about the worst case? Right? You're probably not going to pick the extremes for really large n, but you're also probably not going to pick in the middle, right? What makes this question even more complicated is like, well, what if I picked a really good pivot first and then a really bad pivot next? Or if I picked a really bad pivot first and then a really good pivot next? Like, how does one choice affect later choices? Right? Even worrying about one choice seems complicated, but then worrying about the recursion and how one choice affects the others is just like a world of hurt, right? So how do we sort of cut through, all of these complicated things? If you think about what's going on, it's like really complicated. Okay. All right. So our saving grace again is that we're only interested in the average running time. An average running time is sort of like an aggregate kind of thing. And it's going to actually sort of let us ignore some of the really detailed stuff. We won't have to look at it in such a detailed way when we're trying to calculate the average running time. Okay, so the average running time, okay, the expected value of the running time, is, okay, that's just the formula. All right, so how do we calculate the average running time? Okay. This seems kind of tricky, but we're going to use, okay, well, actually, anyone have any fun ideas? I think this analysis is quite non-trivial, although simpler in hindsight. Any ideas of how to try to analyze the expected running time of quicksort? Yeah. Yeah, I feel like there's like a bunch of words thrown in, and at the end there was expected runtime. But okay. But actually, there's some truth to what you're saying. But there was this idea of like, oh, can we look at the elements separately? I mean, is there some way to pull out small parts that are easier to analyze, and maybe I could sum them all together or something at the end? So we are still going to follow that format. It's slightly different than one element at a time, We're going to look at pairs of elements. Okay, so the total running time of quicksort is basically the total number of comparisons made by the algorithm, right? Plus maybe a constant or something. So we're just going to try to analyze the total number of comparisons made. And in particular, I can say, oh, element number 10 and element number 20, were they compared to each other? Element number 10, element number 21, were they compared to each other? And stuff like that. And then maybe sum them all up. Okay. So for every two indices I less than j, I'll make a variable xij. It's equal to 1 if the ith largest number is compared to the jth largest number, and 0 if it's not. So the sum of xij's will give me the total number of comparisons. Oops. The sum of xij's will capture the total number of comparisons made by the algorithm, and that's basically the running time. All right, so what I want, right? What we want is we want to calculate the expected sum of xij's. That would be the average number of comparisons, and that's basically the average running time. Okay, but in this form, right, the sum of xij's inside the expectation, there's like a full complicated algorithm with the xij's depending on each other, right? So what's the first step toward making this simpler to analyze? Yeah, okay, it's the same thing. Okay, this is the big theme of the class. Where'd it go? Okay. All right, so because we're interested only in the averages, right? The average of the sum is the sum of averages. This is so powerful. So I can write, it's the sum over all pairs I and j, the expected value of xij. But what just happened? On the left, I have the expected number of comparisons made by the algorithm. That's a complicated beast, right? I have no idea if like one comparison early on affects other comparisons later on, and as a, one connected thing. It's impossible, right? But on the right, I've broken it up into the sum, where I'm just saying, hey, what are the odds that this element's compared to that element? This element's compared to that element. And I'm not worried about one comparison affecting other comparisons. I'm not worried about like the order of steps made by this algorithm. Okay? So once you've kind of figured out how to frame and then apply linear of expectation, you've really taken a complicated kind of organic algorithm doing crazy stuff and broken it down into tiny pieces that you can actually analyze. Okay? This is like amazing. So, all right, let's see. All right, now we can analyze one of these by itself. If I can analyze one, then hopefully it won't be very hard to sum things up at the end. So now I just have to analyze one, right? I'm no longer analyzing a whole algorithm. I'm just saying I fixed I and j. What are the odds? What's the probability of it? What's the expected value? So, all right, so the expected value of xij, since it's a 1-0 variable, is the probability that element I is compared to element j. Okay? All right. So that's all we have to answer. How do I figure out the probability that element I is compared to element j? I want to come up with like a different way of looking at it. Any ideas? Okay. So I and j are somewhere here. And over the course of the algorithm, I'm picking all these different pivots, right? And if I pick I, then it'll get compared to j. And if I pick j, it'll get compared to I. If I pick something smaller than I, then it'll just go to the next round where we'll see if some pivot gets picked. If I pick something bigger than j, it'll just survive till the next round. If I pick a pivot in between I and j, it'll split them apart and they'll never get compared. So the real question is just, out of all the elements between I and j, what are the odds that I or j is the first one picked as a pivot? Because over the course of the algorithm, you're picking these pivots, either survive to the next round or they get separated. Okay. Now, between I and j, all of these elements have an equal chance of being picked first as a pivot. Sure. So if you picked something bigger than j as a pivot, then they'll just survive into the next subproblem. It's like nothing happened. And then you keep playing the game until someone gets picked. And each round, everyone has an equal chance being picked. So all of these elements have an equal chance, right? So the odds that I or j is the first out of those j minus I plus 1 elements being picked is 2 over j minus I plus 1. Okay? So the expected value of xij is 2 over j minus I plus 1. So, there's some cleverness, but it's relatively simpler to analyze than trying to analyze an entire algorithm and interactions and all that, right? So, and this is where we'll end. I won't do the high probability because we're over time. Okay, so now we're going back to I want the total number of comparisons, expected number of comparisons. We know the first step is to apply linear of expectation. Okay, we break that down. Now let me plug in this quantity we just calculated. Okay, so I'm summing over all ij, this 2 over j minus I plus 1 that we just figured out. Okay, this is sort of messy, right? How do I estimate this quantity? Anyone have any tricks? Okay, it gets a little bit easier if you interchange sums. So I switch the order of j and I. So now for each j, that's the bigger one, you have all the different i's. Okay, so it's 2 over j minus I, so minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. Okay, so that means you really have kind of 2 over 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 all the way up to 1 over j. Okay, so you have something like this. So 1 over j, okay, it could be at most going up to 1 over n. Right, so you get something like this, 2 over 2n times 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 and so forth. And then what's that? Log n. This is that harmonic sum, right? I think we've seen it a few times before, hopefully. So that second part, 1 over 1, 1 over 2, all the way up to 1 over n, is roughly log n. Okay? And you walk away with n log n in expectation. Okay, so that's how you get n log n expectation. For lack of time, I won't do high probability, but it's not so hard. So I encourage you to take a look in the notes. It's only half a page or something. I probably won't do it next time. I'd rather do a different topic. So, but take a look and it'll show you that with really, really high probability, it'll be at most n log n. And you'll never really see any deviation from that. All right, thanks guys.